Swayam Prabha. Digital India. Educated India.
Hi, thank you everyone for having me here, especially the organizers, Professor Arnan and Professor Raj, for extending this invitation so that I can share my work. The stage has already been set quite high for the talk, so I'll try my best to match it. Today, I will talk about investigating molecules of astrochemical interest using rotational and infrared spectroscopy. I do understand there's a lot of computational talks, but as my previous speaker, I'm also an experimentalist, so please bear with me. So yes, my outline of the talk would be, I'll try to introduce you to the concept of interstellar medium where actually everything happens and the techniques that I've used in the last 6 years and how I plan to move forward with it. So as a first step, what is interstellar medium? It is the vast space between the stars. And this is actually where most of your reactions happen, starting from gas phase and gas grain models, because it's consisting of mostly gases and the dust particles. And the field astrochemistry that is related with it is actually the study of these molecules that are formed or these reactions that we can probe using spectroscopy. So if you look at it, which I have to go again here because this will not work. If you look at the data as of September 2025, you can get this from CDMS website from Cologne. More than 340 molecules have been detected. Now, one thing I would like you to see here, if you look at the graph starting the 1940s to 2020, this paper was published by Brett McGuire in 2022, you see the growth pattern here. It is the mid-1960s actually when the radio astronomy actually began its work, which is meaning you use the laboratory data using rotational spectroscopy and you use the radio telescope, so you collaborate with astronomers and give the data. I'll talk about more why is this technique so important in it, because it's like you're fingerprinting something, and no two people can have the same fingerprint. If you were to go to a voter bank, you can really distinguish each other based on your different fingerprints. So if we move forward with it, you will see that I alone as an experimentalist or the small community of rotational spectroscopists cannot do much, or a small community of theoreticians around the globe cannot do much unless we all collaborate. So you need people who are working in the facilities, you need people who are working in the lab, and you need people who are doing the computations, which experimentalists call them God, because it explains everything. So these detections that has happened over the last, I don't know, say 80 years or so, are mostly rich in the organic molecules like carbon, hydrogen, nitrogen, and oxygen containing species, but the dust particles that are around there are consisting of carbonaceous grains or the silicon grains. And there's a lot of chemistry that happens on top of them. I'll talk about it, but in the scope of this talk, I will talk about these two regions that you see here, the infrared region and the radio wave region. And you see why do I talk about it? Because the radio waves, you can really use the radio telescopes data because the radio waves are emitted right from the space to the ground-based telescopes like GWST, like Atacama Large Millimeter Wave Array or Effelsberg Telescope. I'll talk about it more in the coming slides. So far we have talked about the molecular compositions here, what it is consisting of, and then I will talk about what are the formation mechanisms, right? I have been only doing the experiments that can simulate conditions, but there's so many more mechanisms. For example, the reactions that happen on the surface of ice grains, as you see in this picture, where the carbonaceous, sorry, the resolution is not good for this small size. The carbonaceous or the silicon dust grain and the water molecules condense on top of it, and due to thermal hopping or UV radiation, or if you have a star nearby in the source, these reactions can take place. And of course, then the central part becomes for laboratory experiments where you can do spectroscopy measurements and try to collaborate and see what's out there. I'll talk a bit more about it, how do we do this analysis, but in the meantime, I also want to highlight that not only that we do put the molecule in the setup and try to simulate the conditions and measure it, but we also do plasma chemistry, meaning you put your molecule and then you give around 1500 volts or ranging from 1.2 kV to 1.5 kV, and you blow it apart and see if these two molecules were present in this particular region of space, what could have happened over the years, let's say. And of course, last but not the least, we need the astronomy astronomers, we need people who are working in this to get us the data and try to match it. So let's move on to the next slide. As I said before, for all of these things, potential reaction mechanisms, looking for new molecules in the space, the spectroscopy, the radio astronomy, the experimentals, the laboratory, astrochemistry plays the central part. Can anyone try to fix that while I use this? So I will start with rotational spectroscopy. As you all know, this lies towards the far right-hand side of our electromagnetic spectrum, which ranges from, let's say, 300 megahertz to 300 gigahertz. It's very low in energy, and the idea is to really just excite the rotations of the molecule. So what we actually get from this technique is these A, B, and C that you see here, which are the rotational constants. And why are they so specific, or why are they so useful for us? As I said before, it's like fingerprinting something, because these A, B, and C, all three of them are related to I. This term I is moment of inertia, which directly gives the structural information. So if I were to take a molecule and do isotopic substitution on it, A, B, and C, all three will change. And when you change that, you get a new different spectra. That's how I meant it's fingerprinting. A slightest change in the structure, a slightest change in the conformation, or in the substitution, you would be able to see it. Yes. And based on that, we also do structure analysis. In this crowd, I at least know Arunan, who is he's a pro in the field, if I were to say. I'll talk about it towards the next stage of our talk. Come on. It's going back. 1 second. Okay, so what are the three requisite conditions? In order to measure this, we are limited, or let's say we can only do systems which you can put in gas phase, either by heating them or by laser ablating them, or different techniques that are coming every day now. You need polar molecules. In order to measure rotational spectra, you need your molecule to be polar, which means I will tell you in the next slides, you actually need the macroscopic dipole moment to be formed in order to measure this spectra. And it is so structure sensitive, as I already told you, because if you change the isotopic substitution or you change the conformation, if a bond is like this or this, you will have a different spectra. So I'll lead you through the technique in a bit. So how do we prepare the sample? This is the Parker Series 9 modified valve where you introduce the sample, and it is then supersonically expanded into the chamber, meaning the pressure outside is, say, you're using 3 bar neon as a carrier gas or argon as a carrier gas, depending on what you want and how much cooling you want. The collisions happen between this carrier gas and your molecule of interest. So you have your molecule of interest in your nozzle, and the carrier gas flows through it, takes these vapors into the chamber through a supersonic expansion, meaning the high pressure from the outside expands into the low pressure, say 10 to the minus 12 millibar inside the chamber. This causes the adiabatic expansion, and your molecules cool down to the lowest energy states, as you will see. And once your molecules are coming out of your nozzle, you probe it with a chirp pulse. So for our case, we have been using 2 to 8, then 8 to 18, going on to 110 gigahertz, I'm sorry. And then once your molecules are in this, as I said before, you would create, sorry, I went back actually. You would create a macroscopic dipole moment, meaning all of your molecules will orient in a certain way so that your dipole moment is macroscopic now, sizable enough to be recorded the free induction decay. And once you record the free induction decay, it's in the time domain. You fast Fourier transform it, and you get your spectra looking something like this in the frequency domain. And the next step, of course, is analysis, where I'll spend most of my time now. Okay, so in our lab in Hamburg, we have, I've been clicking the wrong slide always. We have 3 spectrometers. This is the compact spectrometer, which works from 2 to 18 gigahertz. This is 18 to 26 gigahertz, and this is 75 to 110 gigahertz. When I joined my PhD, I was told this is your baby and you have to work with it, because the person before me was just leaving. So in these 2 setups that you see here, we work with supersonic expansions, as I just told you about. So you go to low-lying vibrationally, you go to vibrationally ground state, and you look at the rotational transitions in the low-lying levels. And in the next spectrometer, the room temperature measurement happens, the W-band spectrometer. It's no different in terms of the technique, but you do not expand your molecule supersonically, meaning you do not cool it down, you do not do a directional flow, but instead you fill your chamber with it. So you're looking at very broad signals, and also once you are at 300 Kelvin, say room temperature, based on your Boltzmann distribution, all of your levels are populated. So you not only see your vibrationally ground state, but vibrationally excited states as well. And as I said before, why do we use these instruments? Why am I measuring this? If it has to have some importance or some overlap with the radio telescopes. Otherwise, my data can only be sort of calculated towards this end. So the first two instruments that I talked about overlaps with Effelsberg 100-meter telescope in Germany, which meaning, so you recorded your data here, and they get some data from radio telescopes. You overlap it, and you can just say if it's a detection or a not. But of course, the data that you get from space is not from one molecule. It's extremely, extremely crowded, and it needs some programming and pro theoreticians who do stuff there. That's not my part. I do the experiments. And of course, the W band this is sort of the most prominent one in the field. The Alta-Gamma large millimeter wave array in Chile. It works from 84 to 116 gigahertz, which overlaps directly with 75 to 110 gigahertz that we have in our lab. So you just put these two spectra together and you know if it's a detection and not. But why are we so curious about it? Because it all boils down, we are working like on a small piece of puzzle. It all boils down to how did these reactions happen in space? They're so far apart, the densities are so low, the temperatures are so low. So let's dive more into it and see this. Of course, these are a lot of molecules. I just wanted to show the projects that I've worked on during my PhD and 1 year of postdoc in Hamburg, but there's no time that we can talk all about them. But here I'll talk about this one, 2,4,6 cycloheptatryene 1-carbonitrile. And the reason that I choose this is because 2018 was the first year in the history of radio astronomy that the first signal of an aromatic molecule was detected. Of course, IR spectroscopy did look at the diffuse interstellar bands and other bands that are coming from aromatics, but specific to one molecule in one orientation substituted with cyano group here, this acted like a proxy. If a cyano group is here, then further so many studies came which then showed how a benzene would have reacted with a cyano radical to form this. So this marked actually the way that people went crazy after aromatics and ring molecules in space, because so far we had only seen linear or branched or small molecules. So then in the next 3 years, of course, I was very small by then. And in the next 3 years, I was already in my PhD this time. People started looking at these 5-membered. So if a 6-membered ring is there, how about the 5-membered cyano ring? So we thought as a natural progression, let's look at a 7-membered ring substituted with cyano, just to check limits, right? If there's a 5-membered, if there's a 6-membered cyano substituted, why not a 7-membered? Let's check how far the chemistry is going. And the reason we are using cyano substitution is, 1, it's easy to buy. 2, it has a huge dipole moment. The moment you introduce cyano group to any molecule, you get 4 dpi, 5 dpi, which then gives you a really high signal to noise ratio, as I will show you. So as the first step, where the theoreticians in the group really help you, but we are very good with all of this, all experimentalists can do basic calculations in our group, where we look at the molecules, and as I said before, as I said before, we look at different orientations as well. So if you see the conformer 1, the cyano group is pointing away from you in the back of the screen, and the conformer 2, the cyano group is towards you. So even if these two different conformations, if the group is here or here, you'll get a different spectra. And of course, these 7-membered rings are very prone to cycloheptatryene norcadiene rearrangements, where these 7-membered rings rearrange themselves to form a 3-membered ring on top of a 6. So of course, we looked at that. But of course, the 0-point corrected energies were way higher for us to see them in our experiments. But we did see these two, as I will show you now. So if you look at this molecule in the principal axis system, A, B, and C, I labeled it as 1 and 2. And if you remember, sorry, I should show it here. This is the most stable isomer, the 1. And the second one is 6.3 kilojoules per mole higher in energy. So of course, it would change the abundance in the experiment. So if you see here, the top trace in black is the experiment. And the color traces in the bottom are the simulations based on the fitted rotational constants. So of course they don't just fit, you have to spend from days to months to hopefully not years on the analysis to get this. And you see the red trace is very prominent while the blue is very weak. So I will zoom in to see that the blue one is also there. And as I said before, that the technique is very sensitive, meaning that we have such high resolution that not only that you can see this, but if I zoom into a particular region, you can also see hyperfine split structures, meaning when your angular momentum of the molecule couples with the spin of the molecule, because there's a nitrogen, so the spin of nitrogen, which is 1, it couples together to give you a F quantum number, meaning each rotational transition will be split into different components based on the J value. So here, for example, you see 202 to 303, and the one rotational constant is split into 4 components, or here it's split into 5. So the technique is so sensitive, and the resolution in the lower frequency range, at least where we use supersonic expansion, is 15 kilohertz. So you can really see all the dynamics. If your molecule is tunneling, I didn't talk about it, but in the slide where I showed you the molecule, there's an amino naphthalene. So the hydrogens can tunnel like this. There are water tunneling motions that people study. So you can really probe the dynamics of the system that you're looking at. And of course, when I said it's so structure specific that if you change one isotope, you will see it. But here, we did not put a new sample. It's our same sample, and the carbons and nitrogens that I will show you here are in natural abundance. So the natural abundance of carbon is 1.1%, right? Meaning the signal to noise that you get is higher than 100:1, that you can see these in isotopically, you can see these isotopes, isotopologues of this molecule if you were to substitute 1 or 2 or 3. And based on Kreismann's equation, which I will not dive into right now, but we can discuss this later, you can put these, because once you substitute one atom, you will get this different A, B, and C, which will then give you the moment of inertia and hence the position. So you can really get the structure here. And I cannot emphasize this much, there's no better structure than a gas-phase microwave structure, because it has no other interactions. You don't have to account for solvent effects or the crystal structure where there are neighbors pushing into each other. So far we have looked at the data from low frequency region, right? It was beautiful. But if we go to the W band spectrometer that I talked about, which works in room temperature, this looks like a mess. Someone once called it looks like a bird shit. But if you zoom into it, of course, you will see so many transitions, and based on the fitted rotational constants, you can also put it next to the simulations and you see it fits, right? But there's so many more transitions that are not accounted for. Why? Because if you remember, I told you at room temperature, many levels are populated. So not only the vibrationally ground state, but the vibrationally excited states would also be populated. For example, we were able to assign these 4 modes, which is out of the plane bending, the cyano group dancing like this in-plane wagging motion, which some of my group members call it an Indian motion because we do a head like this a lot. Out of the plane wagging motion and the breathing motions, and even 2 overtones. So we were able to assign even 6 vibrationally excited states. Of course, these numbers are too much, but all I wanted to show you here was the A, B, and C will be different for all of them, meaning if your molecule starts to move, if your molecule starts to vibrate, if your molecule changes orientation, these 3 things, A, B, and C, will change. And the fingerprint of the molecule will be completely different. So if you look at this rotational spectroscopy part, we have been able to measure the molecule from 2 to 110 gigahertz, which not only covers one range, but let's say 3 or 4 different telescopes. So then we use this data. It's also published work. I'll show a QR later. You can use this data to look for the molecules. And of course, if you don't find it right now, that doesn't mean it's not there. It may mean we are looking at the wrong region, because as we know, the space is vast. So one thing you have to consider is, oh, where was benzonitrile found, right? Because that was the motivation for this. And where do I look for this? And where are the abundances and densities and temperatures? Also, the background that I've been showing is for Taras molecular cloud, if someone is interested. And then we were able to get the experimental gas phase structure. We assigned the 6 vibrational excited states. Sorry, I forgot to mention this. One may ask, why are we looking at vibrationally excited states? If you found the molecule, what information are you going to get from looking at vibrationally excited states? Because these states act like a thermometer. So as you saw in the previous experiments, when we were in the low frequency supersonic expansion regime, vibrational excited states were not populated, meaning your temperatures were cold enough that all the molecules were in the lowest vibration state. But if you observe any of the vibrational states, it will give you the idea of temperature. What would have been the Boltzmann distribution that mu21 is populated? Or you observe this signal. So it will literally, it does act like a physical thermometer. So if your molecule is detected and you see the vibration excited state, you can actually say, oh, the temperature around this cloud or this region, be it Orion KL or IRC 2016, you will be able to say, oh, this region actually has around 1000 Kelvin, or this is around 3 Kelvin, based on what you find in that region. So all of the data that I've shown in the rotational spectroscopy study for this molecule will directly help astronomers to look for the molecule. Also as a physical chemist to know the structure and how interactions happen, what abundances are there. Okay, so the next part I will go to infrared experiments and electrical discharge sources coupled with it. We have a collaboration in Felix. We wrote a grant and we got it, and we used the free electron lasers for infrared experiments there. Meaning we were, okay, I will quickly go through it. We wanted to see how the molecule will react if you blow it apart, right? If one molecule is there and you blow it apart and give it enough time to form different things, what will happen? Sorry, I'm short of time, so I will just say the technique here. The sample introduction is exactly the same like it was for rotational spectroscopy, but after your nozzle, you attach this piece. It's a Teflon nozzle consisting of 2 copper electrodes, and you put really high voltages, so you blow everything apart. And then you give a tiny, tiny space, this white space here, for chemistry to happen. So here, we blew apart this molecule, which is phenylsilane. The story behind it I can cover maybe in questions, because it's a low dipole moment compound, so you don't see much in discharge experiments of rotational spectroscopy because carbon and silicon have similar electronegativities. But this technique had a single ion sensitivity, so we were able to record a lot of things. So you blow it apart, the molecules go inside through a supersonic expansion, goes through a skimmer, and then travel up to this mass spectrometer, this reflectron. So it is time of flight, resolved IR spectroscopy. Of course, I cannot go into the detail now, but you try to make the resonance of the molecules that are formed so that the ground states depopulates, and then so it's a pump probe technique, as Wester already told about the REMP. So we pump it with the IR so that your molecules are in resonance with the vibrational states, and then you probe it with the UV, which then ionizes it, shoots it up to the time of flight mass spectrometer, and then you get the signal. So if I were to show you the results right now, this is how the spectra look like. So this is phenylsilane discharge on, meaning you're blowing it apart. This is phenylsilane discharge off, meaning when there's no blowing apart. And this is just benzene discharge to just make sure no repetitions are there. So this is the IR spectra that you get in the black trace, and the red traces are the simulations based on what we thought was in there. Of course, no process is as easy as it's shown here. So you actually take one mass, for example, M to Z 134, and you make different orientations, different substitutions onto your molecule, thinking which will fit. And this is just example where I'm showing 6 different species, but only one of them fits. And this is how you will say, okay, this is the molecule that's present there. Of course, we are not doing this blindly. So for example, the mass to charge 184, not only that we found this structure, the simulation of the structure to be really fitting well, but also there's a NIST gas phase spectra available on it. So you know that that level of theory that you're using or the scaling factor that you're using are actually in working together. You're not just blindly putting B3 lib D3, or should I put the dispersion correction or not. You really check if it's working or not. So in total, we were able to identify more than 12 different species that were generated as a result of electrical discharge. So all we did was put phenylsilane in the nozzle, let it evaporate, put a carrier gas that takes it through, blow it apart, and these were the different molecules we were able to see. This work is not published yet, it's in the pipeline. I just sent a draft to my supervisor. This work was also a part of the Rao Prize in 2024 in ISMS when I presented this. And of course, with the advent of James Webb Space Telescope, you can really use this data because the range overlaps. We measured it from 500 centimeter inverse to 3200 centimeter inverse, which covered fingerprints region. And one of the peak that I did not really talk about, okay, where is it going? One of the peak that I did not really talk about was this peak. So this is specific to the silicon hydrogen stretch. So we looked at different molecules, different spectra, different mass numbers, and all we filtered it with saying, is there a peak at around 2200 centimeter inverse? Because that would just tell me if a silicon carbon bond is forming. And that's what I'm interested in, seeing how silicon substitutes into different aromatic systems. So I talked about rotational spectroscopy. I talked about IIUV iron depth spectroscopy, though I did not have the time to go through the technique, which I'll be happy to go. One thing just to say, there are so many things that I could not talk about. For example, I am going to be joining Professor Tobias' group next week, where I'll study the chemistry of clouds and take my expertise of building stuff there. And I haven't talked about the discharge with rotational spectroscopy. These are the things I would love to talk about in the duration of the conference, if any one of you is interested. We also did some ice measurements where you put an aromatic, then deposit a layer of water ice, and then probe it with IR. We did some more experiments where me and another colleague from Austria, Christina, we built a new setup where we can actually do gas phase ice sublimation studies. So we make ices in liquid nitrogen, put it in, shoot it with either krypton lamps or hydrogen lamps, and wait and see if the gas phase molecules are desorbed and studied with rotational spectroscopy. So I would be very happy if any one of you is interested. If you want to look at the work we have published so far, you can scan this code or check the ID. This is my group. This is my professor, Melanie. Anyone who knows her knows that she's really sweet and supporting and would be happy to collaborate if you have ideas. And these are the two amazing dogs in the group. Thank you. Thank you, everyone, and especially the organizers.
Swayam Prabha, Digital India, Educated India.